aperture radiation. Okay, in this problem, here's how we're going to set it up. Let's say here's the origin, and here's the xy plane. Z is sticking up in the air like it normally is in this class. And I have a shape, an arbitrary shape, whatever shape I want. I will call this my aperture A. And think of it as if I have cut it out of some special magical absorber that forces all electric fields to be zero on its surface, except where I have cut it out. And let's say that from behind, I have illuminated using a source and have placed an electric field, an electromagnetic wave, so an electric and magnetic field across this aperture as a function of x and y on the xy plane. It is E, and I'm going to be working exclusively with E in this problem. I could have done H. It doesn't matter. This is a scalar electromagnetics formula, so it's relatively straightforward no matter what. I'm just going to be consistent and use E. And I'm going to put a little diamond subscript because this is polarization independent. This is actually a result from acoustic diffraction theory, just to keep it simple, because it turns out that for these types of problems, in the main beam especially, there's really no difference in the solutions. It doesn't matter if you have an x-polarized wave that you start with. You're going to get an x-polarized wave when you get up into the far field of the main beam. That polarization is going to be approximately preserved. So let's go ahead and just keep that as a diamond. And then this is going to be a function of x and y. I have E, amplitude and phase of a sinusoidal oscillating field. And all along aperture A, this is non-zero. This is my boundary condition. And I basically want to figure out how does that translate into the half space. Well, if you take ECE 6350 with Professor Peterson and you read Professor Smith's book, I believe he has a really nice treatment. You may even have a class period or two where you derive the Kirchhoff-Helmholtz integral theorem. We don't have enough time to do that, much to your satisfaction, no doubt. You don't know how hard it is for electromagnetics professors not to derive something. But we'll just go ahead and take this result as a given, and I'll put it in a format. What I do want to do is use it to work one example that will be near and dear to our hearts, that is the circular field aperture, not unlike a satellite communications Earth station dish or a satellite dish, if you want to put it on the spacecraft. Use them in both instances. And it's really nice because once you work through the example, you see some really beautiful formulas pop out that kind of reinforce what we learned when we first started to talk about antennas and apertures. Okay, so here's our starting point. This is a given. I know my field along some sort of aperture. Maybe it's in front of a dish antenna, a horn antenna, a reflector of some sort, what have you. How does that translate into far field radiation? Well, the Kirchhoff Helmholtz integral theorem, or what I will call it for the rest of the class period, its nickname KHIT. This is the general formula. And this is for the far field. So you recall what the far field condition is. R, my distance away from the origin, is greater than the max of either lambda or d squared over lambda. D squared is the largest distance across the aperture. We're almost always talking about electromagnetically large antennas in the case of KHIT problems, so you can probably even ignore the lambda. This number, d squared over lambda, is always bigger. Dishes are always 10 lambdas or larger. So that means that this would effectively be 100 lambda away to get into the far field. Some of those really big dishes that are used for like radio astronomy, like say the one in Arecibo, Puerto Rico, the far field is measured in kilometers. You got to be in space before you get into the far field. But that's okay because we're listening to stars and radio sources that are much, much farther away than that. So see, even in that instance, you're still in the far field. Okay, so in the far field, my E diamond scalar electric field as a function of r and theta and phi, these are my points of observation. In spherical coordinates. And keep in mind this is above the half space. This is going to be equal to jk cosine theta 2 pi r ex speed to the minus jkr. So r is distance from the origin. K, of course, is wave number, just like it's always been in this class. Theta is elevation angle. You see we have this constant phase taper in space. That's what that means. It's a phasor, but when you put it in the time domain, that's a traveling wave that moves at constant velocity away from the origin. And then you got to multiply by an integration over the aperture A of my given. And since this is a flat aperture in the xy plane, I'm going to write this in xy coordinates. So keep in mind, x prime, y prime are my variables of integration. Try to keep those separate in your mind. You're sliding around. You're using this integral to slide around and pick up all the little Huygens sources created by the E field. And you're seeing how all of them collectively contribute to that point, r theta phi, in the far field. So don't get confused with the multiple positions floating around in this problem. Now, let me just finish out my formula here. And, of course, that's integrated with respect to x and y primes. And you see, I have the exact same Fourier-type integral. Just because we're working with fields and we're doing a Huygens principle type approach, the radiation principle is the same. As I change the shape and the distribution of phases and amplitudes, the pattern is the Fourier transform of that field distribution now, and it obeys the same types of laws. I make it smaller in one dimension. I make the pattern fatter in the other dimension. And so this is our basic starting point for the analysis, the Kirchhoff-Helmholtz integral theorem in electromagnetics. Now, let's go ahead and solve it for this problem. Uniform circular field. So, in this instance, our aperture is going to be a perfect circle centered at the origin with radius capital R. Everything outside that circle is field equals to 0. And everything inside the circle is going to be a constant, E naught. Inside the circle. And so now let's go ahead and set up the integral for this problem. And it turns out that as long as I've got a hefty calculus book handy with a good with a good table of integrals in the back, or if I have access to Wolfram Alpha on my computer, then I can actually analytically solve this problem. It requires a little finesse and something that you guys have maybe seen once or twice in your studies called a Bessel function. Don't be scared. Don't be scared. After a while of working in mathematics, Bessel functions aren't that much more scary than sines and cosines and other transcendental functions. So it's just a matter of getting used to them. So we'll get to that point in a second. Okay. So what we are going to do, we'll take the Kirchhoff-Helmholtz integral theorem, and start dropping in the terms that we need. This is all going to be the same from the previous pane. Times integral. And let's see, because this is a circle, it's actually easiest to do this integration in the cylindrical coordinate system. So my point of observation will be in the spherical coordinate system, r theta phi, and my variables of integration will be in the cylindrical coordinate system, rho prime and phi prime. I got to put the primes on because now I got two phis floating around. They might be confused for the same thing if I call them the same thing, right? But they're not. They're quite different. So let's go ahead and do that. Remember, in this cylindrical coordinate system, I have to integrate from 0 to 2 pi with respect to azimuth, and from 0 to capital R from here. And that'll swing around and pick up all the contributions. My element of integration is a rho prime, d rho prime, d phi prime. This is the element of integration for area. And remember, I've got to have a d rho prime. I also have to have this rho prime whenever I have a d phi prime because I'm integrating over space. D phi prime does not have units of space, though, either. Right? It has units of radians. So I need that to kind of be along for the ride if you remember your freshman calculus. Okay, so what does the integrand look like? Okay, the E diamond, that's easy. We said it's constant, doesn't depend on positional dependence. And so then the rest of this is just exp jk sine theta. I have an x prime, but I'm not integrating with respect to x prime. I'm integrating in the cylindrical coordinate system. In the cylindrical coordinate system, x prime is equal to rho prime times cosine of phi prime. And likewise, y prime is equal to rho prime sine of phi prime. And that's just elemental trig, right? If this is the x direction, the phi angle, phi prime in this problem, is wherever the variable of integration, the angle that makes with respect to the x-axis. And you use trigonometry to get x prime and y prime out of those two cylindrical coordinate variables. So plugging in that result, I get rho prime cosine of phi prime, and I got to multiply that by a cosine of phi without a prime. And then I get rho prime sine of phi prime times sine of phi. Okay, everybody okay with the steps up until now? Pretty straightforward. We're just plopping the given products into our integral. And now let's do a little manipulation, if you will. Okay, my first thing that I notice is that I've got a common rho prime that I can factor out of this expression. There we go. Okay, that's good. Now, I am also going to apply a trig identity. Seared in your brain from your high school trigonometry teacher, perhaps in some of you at least, is the following formula. The difference angle or summation angle formula for a cosine. If I take two things, subtract or add them together with a cosine, and then take the cosine. That's the same as taking the cosine of one times the cosine of other minus the sine of one times the sine of the other. Since there's a negative here, I actually have to flip that minus sign, and it becomes a plus. But you basically take the product of the cosines plus the product of the sines when you take a difference formula like this. Anybody remember that formula? It looks vaguely familiar, right? I don't expect you. I would put in a formula like that on the test. I don't expect you to. I assume that most of you have better things to do than to live your life like college professors and memorize the trigonometry tables. Okay, so that's the first simplification that I'll make. And, let's go ahead and take this constant out. We said this is a constant, so we don't even need to put that in the integration. We can just take this out here. Okay, well, I've done all the simplifying I can. I'm going to actually have to do some real work now and integrate. However, I'm going to make a simplification here. I am integrating from 0 to 2 pi with a phi prime, with respect to phi prime. And the only place that phi prime shows up in this integral is, this is a theta, by the way, is right here. I'm taking cosine phi prime plus this thing over here. Whoops, I'm adding a phi, regular phi to it. And I'm integrating it from 0 to 2 pi. I'm integrating over one entire cycle of the cosine. So does it even matter where I start, what this offset is? I've added a regular phi, and I'm integrating with respect to phi prime. Does it matter what this is? Because I'm integrating from 0 to 2 pi. I'm going to get a whole cycle of this sine, cosine no matter what. There's no other dependency with respect to phi in here. So with impunity, without loss of generality, I could just do that if I wanted to, right? That'll get me all the contributions that I need. And so let me go ahead and simplify even further. Okay, so that's a good simplification. Okay, here comes the next part. This is the part where we got to use the Bessel function. This is a very common integral, exp to the j some constant times cosine of phi prime. If I'm integrating with respect to phi prime, that is a very well-known result. There's a whole class of special functions that people have spent millions of man-hours studying and using, and it's called a Bessel function. How many people have seen a Bessel function in a class before here? What context was it? What class or what problem were you looking at? What was it? Quantum mechanics. Oh, you were doing like wave number functions?
Yeah, hydrogen.
Hydrogen. Yeah, we were using the, what is that? The model that you use, that you treat the electron as if it was in orbit around the, that's it. The hydrogen nuclei. A nice circular orbit. Who else has seen it before? Don't be shy. Oh, yeah. What class did you see it in?
Peterson's EMAG class.
When he did the Kirchhoff-Helmholtz integral theorem in a circular aperture. Dude, what was the problem? Do you remember?
It was 2 years ago. I think we were doing, it was a spatial integral involving antennas. That's all I can remember.
Yeah, that's probably a very similar problem to this one. Who else in a different class? Yeah.
Like on vibrations on the drum head.
Oh, a circular drum head, right? Let's see. Anyone else? Anyone else? What about do you bother with these in aerospace engineering? That's okay. That's okay. We still like them. So do you see what happened? The Bessel function shows up in any problem that has radial symmetry. It's all the time. Waveguides, optical waveguides, you'll see it in that. You'll see it in all sorts of acoustic problems involving circular symmetry. And so the way this is defined, go ahead and pull this down. Let me go ahead and pull this up so we still have access to it. So the Bessel function of 0 order is defined as the following. It's 1 over 2 pi, the integral from 0 to 2 pi, exp to the jx cosine phi d phi. So if you're integrating something from 0 to 2 pi, whatever constant is out in front, that becomes the argument of the Bessel function. This little subscript, 0, is called the order of the Bessel function. You can have an order of any integer. You can even have non-integer orders. But the most common Bessel function, the one that first pops out of real simple circular problems, is usually the 0 order one. And what does the Bessel function look like? Well, it looks a lot like the sinc function. It looks a lot like the sinc function. The only difference, it kind of has the same 1 over x type envelope falling off. It's even valued. The only difference is that the zero crossings are not uniform like the sinc function. But otherwise, you would almost mistake it for the sinc function if you just gave it a casual glance. But as I said, these zero crossings are not uniform. And that's J0 as a function of x on the horizontal axis. Now, of course, there are other Bessel functions. So, for example, I'll just randomly throw this formula on the board. For no good reason, perhaps. There's a first-order Bessel function, and you can solve it by integrating the zero-order Bessel function. And that gives you actually kind of an odd-shaped sinc-type function that has a zero crossing here, but otherwise has semi-regular or irregular zero crossings as the amplitude tapers off to infinity and asymptotically approaches zero. And this would be J1 of x. And there's so many, you could spend a lifetime studying these things. These are all J, ordinary Bessel functions. We use J to denote ordinary Bessel functions. If you change things around slightly, and maybe, for example, if you take the J out of this integral, you get another type of Bessel function called the modified Bessel function. It's usually given an I and has the same subscripts and the same arguments. And then there are spherical Bessel functions and Bessel functions of the second kind. And there's a whole, I guess math PhDs need something to write dissertations about. And so these are all, not to make light of it, these all have their kind of useful niche problems to solve in the physical sciences and the mathematical sciences. But the J's are probably the most important to initially understand as a grad student. You'll probably see them again if you have a career in research or do any advanced engineering when you get out of Georgia Tech. So anyway, that's what they look like. Just think of them as kind of irregular sinc functions. And let's go ahead and solve it with this. Let's go ahead and plug in. We'll integrate the phi prime result using the Bessel function, and that produces the following. E phasor as a function of r, theta, and phi is now, upon simplification, J E naught k cosine theta over r exp minus jkr. D rho prime, j naught k rho prime sine theta. Okay, so that's using the standard Bessel function integral, which is in the back of most good calculus books. But we're still not done yet. We have one more integration to make. Looks like we've got j naught, a constant of k sine theta times rho prime, and I've got to integrate that with respect to rho prime times another rho prime. Do you think that integral is at the back of the calculus book? Does anyone have the back of the calculus book to look this integral up? No? You didn't bring your calculus book to SATCOM class? Oh, where will we find this integral? Oh, it's over there. How convenient. Look, the professor put it on the board already. It just turns a zero-order Bessel function into a first-order Bessel function. Let's go ahead and use that result. I'm going to do a little u substitution here. U equals k rho prime sine theta. du is equal to k d rho prime sine theta. That will basically turn this integral, when I plug that in, I'll go ahead and skip a little steps, let you enjoy the algebra in the privacy of your own home. This is what the final answer is. Okay. And this is actually cosine theta over sine theta. That's really just a cotangent, right? So we could simplify that as a cotangent theta. This is the field. This is actually the final result. This is the magnitude of the field at the point of observation, r, theta, and phi, given that uniform circle of current. If you can plug in what the Bessel function is in a MATLAB or a Mathematica or even in Excel, you can calculate what this is. Every mathematical package has a function for evaluating Bessel functions of just about any type. The J type, for example, in MATLAB, if you want to evaluate that, that's Bessel J built-in function. And I believe the first argument is the order, and then the second argument is the argument of the function as we drawn up there. And the solvers are almost instant. It calculates this almost as if it was a sine or a cosine in MATLAB. So very easy to compute. Okay, so that's the field. But we're not done yet. We need to figure out the antenna parameters like directivity. Just give it, we can, well, let's see. First, we've got to figure out the power. And to do that, we need pointing vector, right? So let's go ahead and do that. The S vector magnitude is going to be basically the magnitude of the E vector squared divided by 2 impedance. Why do we need the impedance? Because really, pointing vector, we said, is electric field times magnetic field. Magnetic field is going to have the same amplitude in the far field as the electric field vector. You just need to divide by eta, the impedance of the medium, to get that value. And of course, these are peak values that we're dealing with. And when we do average pointing vector, we always need a factor of 1/2 to kind of average it over one cycle of the sine wave. That always comes up. So staying consistent with our practices and translating our result over there, what does that provide for us? That says that this is going to be E naught squared, R squared, 2R squared, eta cotangent squared, theta, J sub 1 squared, kr sine theta. Okay. Now, we've got all these fancy formulas on the board. What does it look like? How does this even behave? Well, let's go ahead and normalize it to actually get the directivity first, right? And the way that we did that in a previous problem, when we looked at the Hertzian dipole, we took the pointing vector and we integrated it over 4 pi steradians. And here we would have to integrate cotangent squared of theta and J1 squared theta over 4 pi steradians. That sounds like a very nasty proposition. But we need to do that to figure out the total radiated power so that we can normalize and figure out what the gain is. But for this problem, there's an easier way. There's an easier way. If we invoke a little bit of conservation of power, we can take a shortcut. Remember, this radiation pattern started as a circular aperture with uniform field that was propagating upward and radiating. So if we can figure out how much power is fluxing through that circular aperture, we can figure out what the total field, the total power is radiated. We don't have to do all those nasty integrations. All we need to do is integrate a circle. All we need to do is integrate a circle. So total power through the circle, I mean, if I want to get really fancy, I know I got this circular aperture A. It's a circle of radius R. I must integrate over the aperture 1/2 E times E complex conjugate over eta, the magnetic field. But of course, we know that the field is constant in here. It's a constant E naught. I don't need to do the integration. If it's constant, then I just take E naught squared over 2 eta, which gives me my watts per meter squared fluxing through the circle, and I just multiply it by the area of circle, pi r squared. And that is my total power in the system. That's the power coming up by conservation of power. If the medium is lossless and I'm not losing anything anywhere else, it's got to all radiate into the the upper half plane somehow, and that's what I'll use to normalize my radiated power through the system. Okay, so we're almost done this problem, and we're almost back to a really neat result. We do all this math only to come up with really simple formulas so that we understand the problem. Okay, so the isotropic power, if I were to take that power that we just calculated, P sub t, and radiate it isotropically over 4 pi steradians, it should fall off pt over 4 pi r squared. That should be the average watts per meter squared if that power were isotropically radiated. We've got a pointing vector for our isotropic radiator. We're going to take the actual radiator, which we found up there at the top of that board, and we're going to divide them. The directivity as a function of theta and phi is going to be equal to the magnitude of the actual radiated pointing vector divided by the isotropic pointing vector. And a bunch of math later, this is what I get when all those things cancel. 4 cotangent squared theta j1 squared kr sine theta. So there's my directivity. And if I assume I have a 100% aperture efficiency and 100% radiation efficiency, that's pretty much going to be my gain for this system. Now, when we talk about realistic dishes, we know you can never get 100% realism. And in fact, I'll categorize all of the losses that you can experience and what you should really expect for a dish antenna. Probably aperture efficiencies of closer to like 60% to 80%, 90% if you pour a ton of engineering into it. But this is basically our directivity and a good approximation of a gain for an ideal circular aperture. So what's the peak gain? What's the most gain you could possibly get at the peak? Well, the peak occurs, of course, when you're on the z-axis, when theta is equal to 0. But now we have a problem. I can't even evaluate that problem at 0, right? I got a cotangent of 0, which is infinity. I got a sine of 0, which is 0, and a j1 of 0. We said that also crosses 0 at argument 0. So I've got a 0 times an infinity. This is the job for whenever you came across a problem like that in your calculus class, what did you have to employ to figure it out? L'Hopital's rule, that's right. You had to start taking derivatives of stuff. And there are sometimes easier ways to do this. L'Hopital's rule is actually based on the idea of a Taylor expansion. When you start taking derivatives and knocking off the terms of a Taylor expansion, you kind of move along to the higher order terms. And those are often not, if you do it enough times, that's a resolvable limit. Let's just cut to the case and use small angle approximations to our functions here. Cotangent of theta. Well, tangent of theta, when you get really close to theta is equal to 0, the tangent of theta for theta in radians is approximately theta for small theta. It's basically sine theta over cosine of theta. Cosine theta is 1 when theta gets close to 0, and sine theta is theta when theta gets close to 0. So, of course, 1 over tangent is also going to be 1 over theta. So this is going to be 1 over theta squared for small theta. Likewise, sine theta, that's also approximately equal to theta when theta is small. When J1 is small, it turns out that J1 is approximately equal to 1/2 of its argument, its linear argument. So I'm going to, in this Taylor series approximation, I'm going to approximate this as k squared r squared theta squared over 4. Because it's basically the argument over 2, and I got J1 squared. So that's going to be the small theta approximation. And now, conveniently, the thetas cancel. And the 4's cancel. And what I'm left with is k squared r squared. And so now we see some intuitive antenna engineering principles coming into play. As the circle gets bigger, i.e. the dish gets bigger, my peak gain goes up. In fact, there's a familiar formula here in disguise. We know that wave number is 2 pi over lambda quantity squared. And we know, let me just rearrange this. I got a 2 squared. That's going to give me 4. I'm going to take one of these pi's and 2 of these lambdas and put it out in front. And that leaves me with pi r squared. Where have you seen that formula before? That's a definition of peak gain, right? 4 pi over lambda squared times the aperture. In this case, it's a circular aperture, so we got to do pi r squared. So even after all of that crazy acrobatics and mathematics, what really pops out of the radiation result is this very straightforward formula that says the peak gain is going to vary proportional to the area of the aperture. 4 pi over lambda squared times area. One of the most important formulas in antenna engineering. And so this tells you what the peak gain is. If I were to graph this, as you will for your homework, I beg your pardon? The directivity for this problem, the directivity evaluated at theta equals to 0 is the highest possible gain you could achieve. The actual gain in a realistic antenna will be less than this, because this isn't taking into account radiation efficiencies. But in the world of perfect antennas on the blackboard, gain is equal to directivity, right? Okay. If I were to graph this would be z overhead. I'd have x over here. The result from scalar propagation here is independent of phi. And that's not surprising because I have a circular aperture. No matter how I look at it, it's going to be a circle. And if I were to graph that directivity, I would see something like this. For a given r, I would see a main lobe and then lots of little side lobes with some symmetry about this axis. And the peak gain would be 4 pi over lambda squared times the area. If I made the antenna bigger, what you would find, the peak value would go up. And the half-power beam width would narrow. And then I would get lots more side lobes along the way. So in your assignment that I provide online, what I do is I give you a more realistic taper for your field. So you have a E field across the aperture, and you taper it. So it's, instead of being uniform, it's at a peak in the middle, and then it falls off. And I give you a couple different taper factors. And then I have you calculate this integral again to figure out what is the directivity for these three or four taper scenarios. And you can see, basically, how does size and tapering of the field distribution influence the far field pattern. And there's some really important concepts in antenna engineering that kind of come out of that problem. So it's a good exercise to work through. Unfortunately, because I'm not giving you all uniform tapers, the integrals are slightly more difficult and will require a numerical integration. I don't care how you do it. You can use any package. You can do it automatically by just kind of rectangular integration, just adding up a bunch of points along the function. Do it manually, or use some of the fancy integration packages that are within whatever mathematical software you have access to. I don't care how you integrate it, as long as you get an answer. And it'll be an interesting exercise in compare and contrast